Hi, I'm Hannah Wagner. Today I am analyzing the motion of a falling slinky. The goal of this lab is to model the motion of the bottom of a slinky that is stretched and then released from rest. Specifically, I want to see if my computational model can accurately predict why the bottom stays still for so long. We're using Newton's second law, F net equals change in momentum over time. For the system, which is the bottom of the slinky, there are two distinct phases. Initially, the upward tension from the stretched coils exactly matches the downward force of gravity, meaning the net force is zero. Once the top of the slinky reaches the bottom, the collapse time, the tension vanishes, and the system falls under the influence of gravity and air drag. I used video analysis to extract the position of the bottom of the slinky. My initial position was 1.75 meters and the mass was 0.218 kilograms. I identified the collapse time at approximately 5.53 seconds. In my code, I used a quadratic drag model, FD equals negative B, the magnitude of B squared, times V hat, with the drag coefficient B of 75 to match the terminal velocity observed in the video. Here is my Python code. I used a while loop to iterate through time. The key logic here is the if statement. If the time t is less than my collapse time, the net force is set to a zero vector. After that time, the code calculates the weight and drag to update the velocity and position using the velocity Verlet or Euler method. Looking at my results, we can see a strong correlation between the experiment and the model. In the experimental graph, the bottom of the slinky remains at a constant position of approximately 0.5 meters for the first 0.6 seconds of the clip. My computational model mirrors this behavior perfectly. The position remains at zero, representing the initial equilibrium state until the collapse time is reached. The primary difference lies in the motion after the collapse. In the model, the descent is a smooth curve dictated by the constant force of gravity and the calculated drag. In the tracker data, you can see a slight stair-step pattern. This is likely due to the slinky's internal oscillations. As it falls, it isn't just a solid mass, it's still compressing and expanding, which causes the center of the mass of the bottom coil to shift slightly relative to our tracking point. Why does the bottom of the slinky stay stationary even though the person has let go of the top? It comes down to the tension force. When the slinky is hanging, it is stretched to a point where the upward tension force Ft exactly equals the downward gravitational force Fg. When the top is released, the information that the tension has changed travels as a longitudinal wave down the slinky at a specific speed. Until that wave reaches the very bottom, the bottom coil still feels the same upward pull from the coils immediately above it. Therefore, the net force remains zero and it stays suspended in mid-air, defying gravity for a brief moment, until the rest of the slinky catches up.